Right. We are at our second talk. Welcome formally. We will talk about some results on quantum Gibbs samplers simulation convergence.
Okay, so thank you very much for the invitation and introduction. So I'm happy to share some recent research results. So which is based on the joint work with G and Lin and Zhenfeng. So in principle, I will cover two works. And the first part is about the efficient quantum samplers with child balance conditions, and second part is about the quantum space-time bound inequalities for the hypocoercive Lindblad dynamics. So hopefully it can provide some complementary information to Gillian's and Fang's talk. Okay, so probably we start from the first part. And the ideas the so-called quantum Gibbs samplers try to prepare quantum Gibbs state on quantum computers, and which is motivated by many aspects. So for example, it can help us to investigate the low temperature and zero temperature physics, and also a substep for many classical quantum algorithms. For example, it can be used as a step as quantum STP solvers, and also as discussed yesterday, a candidate for the quantum computational advantage. So this is the current result, just a quick review, and it's already being discussed in Gillian's talk, so I'll skip it here. In particular, in the last several papers discussed in the first two talks of this workshop. So here we mainly focus on, based on Anthony's and Gillian's papers, try to prepare Gibbs state using the quantum Markov semigroup, that is the Lindblad dynamics, in analog with the classical Gibbs sampling. So the so-called quantum Markov semigroup is just a semigroup of the quantum channels, that is the CPTP maps. It usually involves two parts. The first part is the coherent part, and second part is the dissipative part. So the dissipative part somehow describes the influence from the environment on the subsystem. So it gives the coherence of the system. So that's why you can expect some convergence. And just some quick notations. Okay, so usually we use a dagger for the shooting of pictures. So the main purpose is to try to design some Lindbladian that so that the dynamics is primitive, or you can also say that it's ergodic or reusability. So which means that we start from any state, it can eventually converge to the Gibbs state when time goes to infinity. And the second requirement is that we hope this dynamic can be efficiently simulated on quantum computer. And so the first is that here the ergodicity is somehow equivalent to the unique fixed point properties. So that is we only need to guarantee that the Gibbs state is a unique solution of these equations. But here the quick remark is that here the equivalence requires that the Gibbs state is a full rank. So which means that if we just consider the ground state, and even the ground state is a unique fixed point of these equations, and somehow it's a unique solutions of these equations, then the dynamic may still not converge eventually to the ground state. And so this is the basic definition of the mixing time, and the total cost is somehow just reduced, is somehow just guaranteed by the simulation cost of the Lindblad dynamics. So that is the simulation cost per each time times the mixing time. Here maybe a quick remark is that, so here the efficiency simply is in terms of the simulation part. That is, we hope this part is efficient, and for this part, and we just assume that we know it. And in practice, the total cost depends on both parts. So we have to discuss the scaling, the mixing time. But in the current setting, we mainly focus on the first part. That is the simulation cost somehow has a good scaling. And this has also been discussed in many previous talks. So in generally, the current motivation is mainly from the classical sampling. That is, we try to start from a self-joint generator to random generate some samples and then reject it with certain probabilities. This corresponds to modify the generator to the following form. So here probably emphasize several points. So the first one is the when temperature goes to infinity and the Gibbs state will reduce to the uniform distribution. So somehow the self-joint generators can be regarded as the infinite temperature Gibbs samplers, and this modification step just try to modify this infinite temperature Gibbs samplers to the finite temperature one. Okay. And second point is that, so here we can see that in these modifications, we only involve the ratio between the measure on two different stats. So the reason is that because the partition function is usually hard to estimate, so somehow we always try to avoid this. That's why we use this ratio for, because the partition function will directly cancel. To compute it, we only need to evaluate the energy on state I and j. And we can also see that in the quantum setting, this part is actually just corresponds to the Bohr frequency. That is the energy difference between the Hamiltonian. So that's why in the current formulations, the Bohr frequency is almost everywhere. And finally, I mentioned these symmetry conditions. So these symmetry conditions actually just try to guarantee that the modified generators is detailed and balanced with respect to the Gibbs measure. So it can help us guarantee that the measure is stationary. In the quantum setting, the question is like, can we find a way to modify infinite temperature Gibbs samplers to a finite temperature one? So the reason is that infinite temperature is always easy to construct. To see this, we have to have a quick recall of the quantum detailed balance. So usually in current literature, we only have the two most convenient or two most common detailed balance conditions. And that's meaning because in the quantum setting, the operator is non-commutative, so there are many ways to define detailed balance. Detailed balance means that the generator is self-joined with respect to some inner product induced by the Gibbs state. So the general S1 means that the Gibbs state is evolved like this one, and for the Chem S1, that means that Gibbs state had this symmetry form involved in the inner product. And also similarly in the classical setting, once we have the detailed balance conditions, we can guarantee that the sigma beta is an invariant state. And when temperature goes to infinity, that is beta goes to 0, then the sigma beta just the maximally mixed state and proportional to the identity. So in this case, both detailed balance reduced to the fact that the generator L is a symmetry on the standard like the trace norm inner product. So this means that any symmetry Lindbladian can be regarded as an infinite temperature Gibbs samplers. For such kind of Lindbladian, there's a very convenient canonical form. So we only need to set coherent term to be 0, and then all the jump operators to be self-joined. Then all these Lindbladian can be regarded as like the infinite temperature Gibbs samplers. Then the question reduced to, once we have such a proposed infinite temperature Gibbs samplers, how to modify these jump operators such that the modified generators is satisfy detailed balance conditions for the finite temperature Gibbs samplers, and at the same time, it can be efficiently simulated. And so for here, maybe the quick question is like, what kind of detailed balance we should use? For the generous one, essentially is equivalent to Davis generator up through a coherent term. So Davis generator is already appears a lot of time in this workshop. So essentially, we have to specify some coupling operators satisfy these conditions. So the joint is also in this given set. And then the second condition is that the weighting functions involved in the Lindbladian have to satisfy these KMS conditions, some kind of symmetry conditions. And third is that jump operators has to be the Fourier component of the Hessenberg evolution of this of these coupling operators. So essentially, we just do the decomposition of H, and then a simple compilation give us this one. So here, BH is the Bohr frequency. That is the difference of the energy level of the hypotonian. And clearly, we can also represent the jump operators by the eigen projections of the Hamiltonian associated with lambda. So from these representations, we can clearly see that these jump operators can help us to transition the eigenvectors associated with energy E to energy E plus nu. So it just so somehow it's an achieve transition around the single Bohr frequency. And we'll see that in the KMS case, in somehow we can achieve the transition for multiple Bohr frequency. However, is to simulate these jump operators, we only have two choices. Either we do the decomposition, or the other say somehow in the dual perspective, we do the infinite time Hamiltonian simulations, that is try to compute this integral. And so usually this works if we consider local commuting Hamiltonians and with the local A, because in this case, we can see that we only need to resolve somehow the local energy of the Hamiltonian. So this can be efficiently computed. However, generally, if you consider non-local, consider local non-commuting Hamiltonians, and the energy difference could be very small. So in this case, the computation could be impractical due to energy time principle. It's already pointed out in the Anthony's original papers. So here our focus is just the KMS detailed imbalance conditions, which is strictly weaker than the GNS one. That is, we can construct some examples satisfying the KMS detailed imbalance conditions, but it's not GNS detailed imbalance.
Sorry, so what do you mean by it's impractical in the general non-commuting case? Can you say more?
You mean this one?
Yeah.
Because in the general, so in this case, we can just see from here. So if A is local, then H is local commuting, then this can be reduced to the local terms interact with AJ. So in this case, we only need to resolve the local energies of the Hamiltonian. But if you consider non-local or consider non-commuting Hamiltonians, generally we can simplify it. So we have to resolve all the energies of the Hamiltonian. So generally it's very hard.
Okay.
So sorry. You're using the word called infinite temperature jump orbit.
Yes.
I'm not familiar with this.
So it simply means this sample is just try to sample in the uniform measure, right? So you just like whatever the Gibbs measure is, we can just like the beta goes to infinity or beta goes to 0, then it's just reduced to the uniform measure. So I just call it infinite temperature.
And you're saying that any jump over the A would do.
And in this case, we can just choose self-joint operators, any self-joint operators. In this case, we can guarantee that it's the generator is symmetric, so it's automatically works.
Yes, it's symmetric with respect to the plane Hilbert-Schmidt inner product, which means sigma is identical.
So for time reason, I just directly give the constructions. So essentially, as mentioned, the infinite temperature in the quantum case, the infinite temperature samplers only need to specify some self-joint operators or some proposed jump. So just defined here. For example, in the practice, we can just take them as the Pauli matrix. And then for the questions like we want to modify it, satisfy the modified generator is going to be symmetry for the finite temperature Gibbs state. So in this case, we choose to do it this way. So you just this strategy is just like the reweighted strategy mentioned in the Gillian's talk. So we just decompose each given self-joint operators according to the Bohr frequency. Then we add some weight here, and here we need to specify these weight functions. Somehow we can also call it filtering functions by these symmetry conditions. So these symmetry conditions is also just the analog of the in the classical setting, that is GR equals to RG1 over R something. So these two conditions will guarantee that these jump operators will somehow be involved in the KMS conditions. And the second sentence, then we also need to construct a coherent term. So for the KMS determinant conditions, according to the canonical form, then this coherent term can be uniquely determined by these jump operators. So once we define the jump operators, then the coherent term can be uniquely determined. So basically this is only things we need to construct. Okay, this is just a quick summary of the constructions. So here we suppose we have a given jump operators, then we define filtering functions, satisfy some symmetry conditions, then we plug into the general form of the Lindbladian with the coherent term and jump operators. So these generators will satisfy the KMS conditions, and so which automatically has the Gibbs state as the invariant state. So this is the construction is based on the canonic form of the Lindbladian with the KMS conditions, which has already been discussed maybe 70 years ago. And here just a quick remark. So we can see that for KMS detailed imbalance conditions, this coherent term is necessary. Well, for the GNS one, there's no coherent term. So this is the first difference. And also here we only need involve one jump operators. This is simply for the formulations. So in practice, we have to involve multiple jump operators to guarantee that to guarantee that the dynamic is ergodic, so that is it can converge to the invariant state that is this Gibbs state.
Very
very implicit. So it is yeah, that's true.
So implicit makes sense.
It's described in a abstract way, like in system algebra or something. And here, as mentioned, we only need to construct these jump operators and involve the A and F, and A is given by ourselves. So, for example, it's Pauli. So the only thing we need to construct is the function F. Here, the function F, we designed two examples. The first one is like the metropolis type transitions. The second one is the Gaussian type transitions. So essentially, it's involved the function in this way and this way. And so this W is just like truncation function. The practical form is not important. So this is basically the pictures. So the two examples, choosing these two examples just try to means that, so compared to the GNS case, we see that a single jump in somehow it only corresponds to the jump for one single Bohr frequency. But for the ChemMass case, we can see that this can achieve the jump for multiple Bohr frequency. And even the support can remain to be the older one, even in the low temperatures. And for example, in the metropolis type, for the Gaussian case, the support will shrink to 0. But if you consider the other choice, then we can see that the support can be guaranteed to be the older one. So this is somehow it's the major difference between the ChemMass and the GNS case. Okay, so in principle, so we just construct the Gibbs samplers, and based on the given self-joint proposal jump, and also the choice of filter functions, and we assume that this part is primitive. This means that our choice can guarantee that the sigma beta is the unique invariant state of these generators. That's the part to try to discuss the simulation properties. And this is already be reviewed in Shenhao's work. So in principle, we have to guarantee that the block encoding of the jump operators and the coherent term. So this means that we have to efficiently simulate the time integral involving the jump and also the coherent term. So in the previous slides, the coherent term is describing the frequency domain, but we can easily do the Fourier transform to transform into time domain. So essentially, we just need to simulate some time integrals. So to do that, just similar to the classical numerical analysis, we have to assume some regularity and decaying properties, because we need the decaying property to truncate the infinite time integral to a finite time interval, finite interval, and then use somehow the regularity to discretize these integrations. So essentially, these two properties is somehow is necessary if you want to do some efficient computations.
So once you choose the f function according to, for example, the previous slides, and these assumptions are automatically satisfied, right?
These are some technical assumptions to guarantee that the cost has some optimal order, but we have to assume it.
So what I mean is that so if you use a function that you have on the previous slide,
yes,
that automatically satisfies these conditions, right?
Yes, it was. Yes, but
to verify.
yeah, but we have to according to the example to check that it is. And so this is the total cost. So that is if you want to prepare a Gibbs state with some other epsilon, we only need to simulate the quantum Markov semigroup up to the Kim mix, and with the total cost of this one. That is, we run the dynamic to T mix, so it's the old epsilon, and the simulation error is also epsilon, so the total error is epsilon, and the simulation cost of the dynamic of this one. So this part is avoidable, so this is just the running time, and this part is just the simulation cost per each time. So this beta comes from because we want to simulate the Gibbs state, and this quadratic dependence of the number of the jump, it just comes from the quadratic dependence of the Lindbladian on the jump operators. Okay, then this is always appears in the simulation cost. And this is some remarks. So first, in our construction, there's no restrict assumptions for the Hamiltonian. So it could be local, non-local, commuting or non-commuting. So in general, there's no assumptions. And second part, if Hamiltonian is local, and also the coupling operator, that is the self-adjoint operator, is also local. And in this case, we can prove the cozy locality. But this is only for the jump operators. For the coherent term, very likely we need at the high temperatures to prove this cozy locality. And this properties is helpful to prove in the faster mixing at the high temperature for non-commuting local Hamiltonians. This has already been discussed in Castigliano's talk.
Right, can I ask a conceptual question?
Yeah.
So maybe this is naive, but are you not worried that like T mix is only controlled in cases where the Gibbs state is classical? So like one of the things that we proved was that at high enough temperature that the state is separable.
Yeah.
Okay.
No. I know the paper. That's a paper to show that in the high temperature, essentially the Gibbs state is classical, but in this paper the technique is different. It's basically on the perturbation theory. That is, we consider infinite temperature limit. So then it's the fixed point just somewhat just identity, and then we just try to control the perturbations using the stability of the Hamiltonian, stability of the ground state energy gap of the Hamiltonian.
Yeah. So I do think in this paper the temperature is not set high to make the Gibbs state to be classical.
We don't know, right?
I think
it's
a
very much an open question for this community.
Yeah, we don't.
Constant.
Yeah, right.
Yeah.
High enough constant.
I mean, right now the gap is like down to I mean, at least if you have K local, we're talking about like a constant factor gap.
So here first we need first we consider local non-commuting Hamiltonians, and also A is local. In this case, we can show that in the limit, the limit problem is totally local and has the maximum mix state as a fixed point, and then they just try to use the existing result to show that the perturbation somehow can help to guarantee the gap can preserve in the high temperature, but we don't know like whether in temperature high enough the Gibbs state can really decompose the system.
I think like one of the challenges here is that so if you're at low enough temperature,
yes,
then the problem even classically is NP hard.
Yeah.
So somehow the region where it could be like BQP is small.
Whether it's small, we don't, right?
Yeah.
So let's just make sure on the same page in terms of
Yeah.
general belief. So for some canonical systems, high enough constant temperature, that's easy. That's what you do, for example. Low enough temperature, constant temperature is going to be hard. There's going to be a gap, right? And at this point, we don't know where this high enough temperature lies.
Right.
Here is it. We don't know. So it would be great to figure this out by some method. And but it's not quite obvious from, I guess that's what Jian was saying. It's not quite obvious from the proof that that temperature is higher than yours. Let's put it that way. We just don't know.
Yeah. I think we're also more interested in specific systems here, right? So it's not just about
that. Yeah, definitely, I agree.
That's maybe one of the big open questions.
So I mean, specific systems make sense to me, but I mean, otherwise, so I guess my point is that if you look at the locality parameter, right? So even the dependence on what the temperature is in terms of, the locality, the upper and lower bounds for where it becomes NP hard versus where it becomes separable are off by a constant factor.
Right.
So somehow, I don't know, I'm just wondering, should one be worried or?
Sort of, right? Because the NP hard is sort of like QMA hardness. They are in the pretty pathological region. Yeah. That's the hope.
Yeah.
And whether you can find some physically interesting things to push down.
Yeah.
And while avoiding
that I agree.
That'd be very interesting. Yeah. But at this point, the community may not have interest.
Mm-hmm.
So that.
That's good.
Okay, so. That's probably the remark on this part. And
could you say a little bit about your claim is that the locality is useful in proving the mixing time power? Could you say a little bit about how it appears in the
essentially because so it's similar to Tony's talk. So we have to transform this problem to the parent Hamiltonian, and then the problem just like reduced to the stability of the Hamiltonian, the Bronsted energy of the Hamiltonian. So in that part, there's a paper to show that if the limiting case, the edge has some like the frustration free and also have some properties, and then if the perturbation is quasi-local, then we can guarantee that so that's why we discuss okay, so this is the concluding remarks of the first part. So essentially, we propose the efficient and simulatable quantitative samplers with determined balance conditions with this cost. So this cost is similar to Antonius and Gillian's work. Okay, but in practice, the performance will highly depends on the mixing time. So and this is probably more important in the practice. And here the open question is like because I mentioned in the one major difference between the KMS and GNS is that GNS can only achieve a single transition for the Boyer frequency. That, for example, you look at the Davis generators and eigenvectors of the Hamiltonian, then it's just reduced to the classical Markov chain. But it is not the case for the KMS one. So if you just add the KMS samplers on the eigenvectors, it will directly give some off-diagonal terms. So in that sense, somehow the KMS case can be more quantum. So we can expect that it's probably more helpful in the mixing time. So the question is like, can we find Hamiltonian such that we can find the KMS samplers, which is mixing faster than any GNS one? Probably this question is more ambitious because we claim it's any, but I think any partial solutions for this question is probably helpful to understanding the difference between the KMS and GNS case. Because the GNS is essentially the Davis generator, but the KMS will have much more freedom. Okay, so this is the reference. Right. So maybe in the last 15 or 20 minutes, we discussed the quantum space Bangakan inequality for the hypocoercive Lindblad dynamics, which is somehow is an Antonian framework for the Neapolov functional approach discussed in this talk. So essentially, we want to estimate the convergence rate, and that is the mixing time. And here we will try to focus on the functional inequality perspective. Essentially, there's no too much difference between the functional inequality and the Neapolov functional perspective because the functional inequality somehow naturally corresponds to some Neapolov functionals. Okay, so this is the basic result for the mixing time. That is, assume the determinant balance. We can use the spectrum gap to prove the faster mixing if the gap is independent of the system size, and if the second approach is based on the modified log-Sobolev inequality. That is if the constant is dependent on the system size, then we have the rapid mixing. That is log n log n. Here n is not the number of qubits; it's just the total dimension. So maybe the more important question is like when we have this system size independent constant, that is when we have this uniform spectrum gap and modified log-Sobolev constant. So this. Yeah, sure. So essentially, you just need this gap is somehow comparable to discrete factors to become the same one. So for example, you can show that. For example, if this one just has a log and decay, then this is totally fine. And so then when we have the uniform spectrum gap, so essentially for these questions, we have to connect, at least in the current literature, we have to connect the dynamic properties to the static properties of the Gibbs state. For example, covariance, correlations, and also the mutual information of the static static properties of the Gibbs state. And this is basically the current result we have. For the Davis generator with local commuting, there's many results, but for the local non-commuting case, we only aware this is probably the only work we have. And also in the SAS community, there's also a paper in the high temperature case. So in this part, the main focus is try to design some approaches to dealing with the dynamic without the Italian balance conditions. And so this is the basic setup. Suppose we have a Lindbladian, which is K-mass Italian balance, and then we add a coherent term with this Hamiltonian commute with the Gibbs state, and at this part will directly break the Italian balance conditions. Okay? And this can be directly checked by definition. So here we still assume the ergodicity, that is the dynamic will converge to the Gibbs state when t goes to infinity. And here a remark is that we can think this problem has a similar structure for the kinetic Fock-Planck equations, that is the underdamped Lagrangian dynamics. So here I will not give a very preset the correspondence between them. So maybe the rigorous proof can be found in this one. So it's discussed in the semi-classical setting. So here just quickly comment the structure between these two problems. So first, we look at this dissipative part. So this is the gradient flow structures. And we can see that in the quantum case, these Italian balance conditions can also guarantee some gradient flow structures. For example, GNS can help us to prove this is the gradient flow for some relative entropy in some quantum Wasserstein space. And similar for K-mass, we can show that this is the gradient flow for the Cascade divergence. And for the coherent part, essentially this is just this coherent term here, and this is just the Hamiltonian flow. So both of this part has the energy preserving properties. So essentially you have the gradient flow, which gives us the dissipation, and we have the energy conservation part before it. So this is just a quick remark. So the main purpose of this talk is try to give a convergence estimate of L2 norm. This can be, if you translate this part to the quantum state level, just in the Schrödinger picture, that is the Cascade divergence. Just convergence in the Cascade divergence. And this can be directly translated to the mixing time by the standard approach. So here we only focus on convergence rate here. So from the standard ODE theory, we know that because Lindblad is simply an ODE. So by standard ODE theory, we know that the sharp convergence rate here is just given by the spectrum gap. But here, because we don't have the Italian balance, so the spectrum could be complex, but we can still define the spectrum gap. That is somehow the infinite, somehow just consider real part and then take the infimum here. That is the one close to the 0 point. So this is just quite general theory, and now I'll show some generic result for this convergence rate here. That is the spectrum gap. So essentially, we can show that adding coherent term can, in general, accelerate the convergence by increasing the spectrum gap. So here this is the setup. So this is set by similar as before, but we just add a coupling, just somehow add a scaling parameter alpha here. Okay. And this is just some basic notations. We denote decay is the Bohr frequency associated with the coherent term k here. And then we denote the eigenspace B nu, just be the eigenspace of this coherent term associated with the Bohr frequency. But we add additional normalized conditions. And then we denote it by lambda nu as the minimum energy of the dissipative part restricted on this eigenspace. So just restrict the input here into this eigenspace. Okay. So these are some basic notations: decay, B nu, and lambda nu. So this is the first result that we can show that spectrum gap is always increased if add this coherent term. And maybe the more important thing is like when the spectrum gap, when the inequality is strict. And so for this, is if and only if this following condition can be satisfied. So here B nu is just a sequence of eigenfunctions associated with the coherent term here. And here BD is the eigenspace for the gap. So here the gap is somehow just the smallest non-zero eigenvalue of these positive operators. So it's clearly that the eigenspace. And then we only need to guarantee that these two eigenspace has no intersection. Okay. And then we can also show that if the alpha goes to infinity, the spectrum gap will converge to the quantities that is the infimum of lambda nu. So here maybe the remark is that if we can prove the strictly inequality for one of alpha, and then it automatically holds for all alpha, and then if you take alpha goes to infinity, that is this quantity, we are still strictly greater than lambda LD. The reason is that this condition is independent of alpha, and so it's easy to prove that the gap will be guaranteed if alpha goes to, the strict increase will still be held when alpha goes to infinity.
What is it? What is the Speak louder. So as alpha goes to infinity, the special gap is the equal of lambda nu.
Yes. The lambda nu is just defined by the minimum energy of the dissipative part restricted on each eigenspace associated with the Bohr frequency. So it's defined here.
So what's this?
What's this? This just so this is subjoint operators. So we just restrict on. So this just simply minimization problem.
It simply mean what?
This just simply variational problem, minimization problem. So we can find the minimal energy here.
Is LK a normal operator?
LK, yes, it's a normal operator.
So you don't pay anything in the eigenvectors when you do this. It could be because if it was non-normal, then you would not get a good convergence result just from having special things.
Yes, because K is subjoint, so somehow these operators would be, so the eigenvalues was real and K is subjoint.
But L alpha may not be normal.
Sorry, that's what I'm asking. So L
Yeah, I
alpha
think
is
you're
not
asking.
self-adjoint, right?
Yeah, it's not.
L alpha, oh yeah, that's
You might still need to pay.
You might, I think.
The
You
spectral
don't
gap.
know that it's normal.
Yeah, spectral gap is defined as a real part.
yeah, sorry.
I'm asking about the eigenvectors.
Yeah. You still need to pay in terms of the big constant C.
So it could be that as you increase alpha, that big constant also increases,
That could,
and your mixing actually doesn't get better.
I think that. So you increase alpha, it's not clear a priori whether you need to pay a big factor in terms of the constant C. The C may depend on alpha.
Yeah.
But in the infinite time limit, you will gain. Yeah, we're talking about asymptotic rate because we're talking about spectral gap. Asymptotic rate is strictly
Not
Yes, the prefactor C, that's true. Yeah, prefactor C.
So you have this statement that alpha go to infinity, spectral gap converge. Does it mean that alpha, the bigger the alpha, the better?
Maybe not. Here, yeah, the answer is maybe not. Yeah, this is not strictly increase in alpha. Yeah, we can only this just for each alpha is greater. It's not increasing alpha.
So just to clarify, so the asymptotic rate is certainly increasing but for fixed precision, it is not clear the mixing time has to increase.
Yeah.
That's more required.
If you're asking this factor.
Yeah.
Okay, so in general, the direct explanation of the spectrum gap in lambda is generally hard, and so and a quick way to do that if LD is coercive, so that is this part, the kernel is trivial, and then we can just consider symmetrize the Lindbladian. That is just by take L dagger plus L and over 2, and this will directly give LD, and this part is good. So in this case, we can, so the spectrum gap of these self-joint operators will work. So this is already mentioned in the from this talk by a simple ODE case. So the question is like, what is the kernel LD is non-trivial. So in this case, we focus on the hypocoercive case. That is, the kernel is greater than 1. So essentially, we can put this as a definition of the hypocoercivity. Here, the quick observation is that even the LD may not be coercive on the whole space, but at least it is coercive on the subspace, that is the kernel, that is also the complement of the kernel of this one. And the reason is that because minus LD just a self-joint operators, so it's clearly, and it's a non-negative self-joint operator, so it's always positive on the range of these operators. So essentially that's this condition. This is always true because we consider finite dimensional case. So the main difficulty is that based on these observations, the dissipation only happens on the subspace. So we can have the total convergence. So we don't have the dissipation on the whole space. So we can have the convergence rate directly from this coercivity. So that's the main problem. And yeah. And to continue, we have to add some additional assumptions. That is, suppose this one, that is the pi 0 is the projection to the kernel of LD. And then we have these conditions. And this assumption has been discussed yesterday. Essentially, this is just a technical assumption. Very likely for the result, this can be removed. But in the current setup, we choose to keep it. And once we have these assumptions and based on the primitivity of the whole dynamics, and we can show that these operators associated with the coherent term is coercive on the kernel LD. So we can see that these two conditions simply means that we have operators which are coercive on the orthogonal complement of kernel LD, and the other part, we have another operator which is coercive on the kernel LD. So essentially, we have two operators which is coercive on two orthogonal complement subspaces. So we can expect based on these two conditions, we can prove the convergence on the whole space. So this is basically the main result. So here, so essentially, we can prove that on the above assumptions, the convergence can be guaranteed of this form. That is C0 E minus mu t here, and C0 is always greater than 1. And here remark is that this part is a uniform constant. So it's independent of any constant, any parameters. So it's just a uniform constant, maybe like 2 or 3 or 5. Okay, it is independent of the system. And here the convergence rate nu here, it depends on the factor, the constant lambda d and sk defined before, and also some operator norms. If you consider some asymptotical regime, this can be simplified a lot. The quick remark is that this prefactor is greater than 1. It's just a consequence of the hypocoercivity. So essentially, if C0 equal to 1, then the system just be coercive. It's unavoidable. And finally, mention that this part is fully explicit, so it can help us to optimize the convergence rate in terms of the system parameters. We have a quick slides in the later to discuss it. So the proof is based on the vibrational framework based on the space-time Poincare inequality for the underdamped long-term dynamics. So essentially, this is the functional inequality we are going to introduce. So I will not introduce the proof and even explain many of the formulas. Essentially, we just introduce some time average expectations. So this is the standard expectation with respect to the Gibbs state, and then do the time average here. And this is also the time average version of the inner product. So compared to the standard space Poincare inequality, so the main difference is just try to change this L2 norm to the time averaged one introduced by this time averaged inner product. So that's the main difference between the space Poincare and the space-time Poincare. So the essential idea is that because the dissipation works on only on a subspace, so we have to observe for a certain time in order the dissipation propagate to the whole space. So just like Lindblad bound, so the local information will propagate to the whole space up to a finite time. So essentially, this is also happens here. We have to observe for a certain time in order to have the convergence on the whole space. That's why we need to consider this time integral form. And in the several lines, so I will not give the proof of this one, but I will just quickly assume that if this is true, and then we can have a 2 lines proof for the convergence. So essentially, if they have the space-time Poincare inequality, we can prove the purely exponential convergence of the time average L2 functional. So purely exponential convergence, there's no prefactors. So this one will minus exponential minus some convergence rate times the initial conditions, and the convergence rate will be described in this form. So lambda d is just the constant involved in the coercivity of the dissipative part. And these two constants is just from the space-time von Gachet inequality. So that is the more precise we estimate for C1 and C2, and the better result we can have. And then after we have this, then by the standard, the constructivity of the dynamics, and we can transform this convergence back to the original L2 norm. And at the same time, we can optimize the length of, because there's a T involved here. So a direct translation, well, such that the convergence rate involved in T. However, the T dependence is explicit, so we can optimize it. And turns out like we need to choose T is proportional to SK inverse. Okay, so this is probably the last slide. So essentially, because our convergence rate is quite explicit, just here, and then we can directly apply to some models involve some scaling parameters. In particular, if you apply our convergence at lower bound of the convergence rate to this model, and we can see that the estimated convergence rate is maximized at gamma of this form. However, if you apply the convergence rate for this model, that is, we add some scaling parameter on the coherent term, we see that convergence rate is always monotonic increase when alpha goes to infinity. So we can see that the scaling difference is very different for alpha and gamma added on different part. Okay, so this is a concluding remarks. Essentially, we show that adding coherent term can in general increase the spectrum gap and accelerate convergence. And we also propose an alternative framework to discuss the convergence of the hypocoercive Lindblad dynamics. So the natural question is like, of course, when we have the systems, when we have the convergence rate is independent of system size. That is, can we connect this estimate also to the static properties of the Gibbs state to have some uniform convergence rate? And the second question is like, can we have more quantitative estimation for the particular physical models? For example, here the acceleration is only quantitative. It's just it is possible to have some accelerations, but we don't know how large it is. So to do that, we have to focus on some specific system to have more accurate estimations. So that's the main open question, and thank you for attention.
Unfortunately, we are short on time. Maybe one very short question.
So can you go back to the scaling part? Yeah, yeah. So the two setups only differ by a rescaling of time.
Yes, that's true. That's true.
So
yes, that's true.
These two differences, how to understand the two qualitatively, supposed to be qualitatively different.
Essentially, but that's true. The proof is essentially just a scaling of the time. We can translate this one to this one.
Yeah. So which one? I mean, clearly one asks you to
This one is
infinity. The others set the optimal gamma. Should the first one be actually used in practice?
Yeah, in principle, you can either prove this one and do the time scaling, then translate to this one. You can also prove this one, then translate to this one by the scaling.
It kind of depends on what you assume by simulation cost, right? Because alpha goes to infinity. If you're a Lindbladian simulator, your cost depends on like linearly with alpha, that you should use the first scale. If you somehow, if your simulation model, the cost is independent of alpha, then the second scaling tells you that you can take as large as alpha you want, and that's the best.
Some sort of like interaction picture.
Yeah, but I mean, because here the simulation model is different from classical dynamics, right? In classical dynamics, then I would argue the first regime is more reasonable because alpha large means the system is very stiff. But I mean, the quantum simulation algorithms could be different. So that's why we can list both of the regime.
What's time for having akin? We convene at 10 minutes past 11.